Раз. Работает, отлично. Okay, so let's start. So let me first recall what we would like to prove, namely the statement of Levi-Shostka theorem. And to this end, let me recall what's going on. So the basic definition. So we will be dealing with the domain D in Cn. For simplicity, everywhere we will assume that it is locally connected at the boundary point. So let us recall that it is locally connected at a boundary point, zeta, if there exists arbitrarily small neighborhood of this point, such that its intersection with D is connected. So, and let us say D. So let us call D. Let D locally connected at zeta is homomorphically non-extendable if there exists homomorphic function. It's homomorphic on the intersection, on the connected intersection. That doesn't extend, so it's holomorphic, and F doesn't extend holomorphically to zeta. And we call that D is locally connected or holomorphically non-extendable at the boundary if this holds for every boundary point. And we have stated Oka's theorem. If D states that two notions are holomorphically, D is domain of holomorphia. If and only if it is holomorphically non-extendable, meaning holomorphically non-extendable at the boundary. And we have introduced yet another notion of convexity. Levi convexity or L convexity. D is called L convex. If for every boundary point for every homomorphic surface, for every compact homomorphic surface S through the boundary point with boundary contained in D for any for any sequence of compact holomorphic surfaces Sk convergent to S with boundaries convergent to the boundaries of S and thus lying in the domain, one has that in this intersection, so Sk are not entirely contained in D for all k big enough. So for every k big enough, the intersection, so the complement to G of the surface is non-empty. So starting from some certain moment, they indeed intersect the complement on D. Of D. That's L convexity. And D is locally L convex. It's modified version of definition which I had introduced during the lecture, but in the notes I have corrected it. Locally N convex at zeta. If there exists arbitrarily small neighborhood of this point such that the intersection of this neighborhood with D is L convex at the given boundary point. And clearly, L convexity at each point implies local convexity, local L convexity. Just going forward, it's obvious. That's it. And we know that the following is true. So we have proved the following theorem. If D is domain of holomorphy, and similarly, D is called locally or globally L convex if this is true for every boundary point. So, first statement is that D is the domain holomorphic. This implies that it is L convex. Second, if D is holomorphically non-extendable, and zeta implies locally L convex at zeta. And next, we have introduced Levy form. We have after this, we have concentrated ourselves to the case, special case. The boundary is C2 smooth. So the special case when D is sublevel set of a function. That's it. And we will, it appears that in this particular case, and so we require also that the differential of phi is non-zero at the level set. This means that the zero level set is some manifold. It's a boundary of D. And this is the main case we will concentrate from now on. In this case, there is no local convexivity problem, so everything is fine. And it appears that there are one necessary condition and one sufficient condition of type of partial derivative inequality, which are conditions for holomorphic non-extendability or local convexity. So let's introduce Levy form. So extended Levy form L. During last lecture, I denoted by L, but it would be more convenient, I think, to denote L by L phi in order to emphasize that we are dealing with the Levy form of the function phi. VB, LV. I don't remember the notation, but yes, that's it. It was like this. Yes. Extended Levy form. It is the sum of d squared phi dz g dz g bar dz g dz k bar. So it is at the point x times vg w bar k. That's it. And we have seen that it's Hermitian form And it has functoriality property. With respect to biholomorphisms, for every local biholomorphism H of W, we have the following. So the Levy form of the composition, we consider that the compositions are well defined, no problem with definition domain. And we evaluate this form at X, and we evaluate it at the pair of vectors VW, and this is equal to the Levy form, extended Levy form of the function phi at the point h of x of the following vectors: dh v and dh w, and over all this we put bar. That's it.
Yeah.
Yes. That's it. And we have introduced the Levy form, the true Levy form. L sub phi. So L sub phi is the extended Levy form, so at point x, restricted to the maximal complex subspace. So what is H? H is maximal complex subspace in the tangent space to the zero locus of phi. So we take with a submanifold, local submanifold phi equals 0. So we assume that, recall that we assume that phi of x is equal to 0. And we take the local submanifold, the 0 level set, and we take the tangent space, which is codimension 1, real codimension 1 hyperplane in complex space. And we take the maximal complex subspace, and we know that H is equal to H is kernel of the C-linear part of the differential phi at x. That's it. We know that. And we know that it is codimension. Its complex codimension is equal to 1 in Cn. And that's the Levy form. And now Levy-Kshostka theorem. States the following. So first, let L Levy form be positive. The Levy form, the extended Levy form restricted to H, be positive definite. Then D is holomorphically non-extendable. At x, sorry. So from now on, we consider that D is as, say, phi less than 0, phi is C2, and the boundary is the zero locus. And the differential of phi is non-zero. That's our assumption. And we consider that x lies there, x lies in the boundary. So it's first statement. And second statement, let D be locally L convex at x. Then the Levy form is non-negative definite at x. So let me recall the following, that we have proved the following. So, so in the proof of statement 1, we will use sufficient condition of holomorphic non-extendability. The following proposition: let x be a boundary point, and let there exist a neighborhood in Cn such that there exists a function on the intersection which is holomorphic. Sorry. A holomorphic function on the whole neighborhood. Yes, on whole neighborhood, such that if this restriction of f to the intersection doesn't vanish at all, and f of x vanishes, then G is holomorphically non-extendable at x. So let me recall that it is proof. The proof is quite obvious. Let us take f tilde, which is 1 over f, and this function is obviously holomorphic on this intersection. It doesn't extend to x. It просто is infinity. And to prove statement 1, we would like to construct such a function. What is zero locus of a function? Zero locus of a function is a hypersurface. And we will construct a regular hypersurface which touches the boundary of D from the outside, like this. And we will just impose it, construct the function which vanishes on this hypersurface, and that's it, will be it. So how to do this? And we will have to define hypersurface, and this will be done by using positivity of Levy form. And so let me recall that we have proved the following proposition: that if U is C2 smooth, then there exist local coordinates. There exist local coordinates means we can change coordinates by applying by holomorphisms. So passing to new local coordinates in which phi of z is equal to the real part of z1 plus Levy form applied to the Euler field plus lower term. That's it. And we will use this. And then it follows that H is Z1. So local coordinate centered at the point X. So Z1 vanishes there. And so, and H is Z1 is equal to 0. To be honest, I should have said dz1 equal to 0 in order to emphasize that it lies in tangent space. For this reason we will, but just for us it will be the same. This is H, this is holomorphic. Sorry?
I believe in Cn there was no difference.
Sorry? Yes, so H is dz1 is equal to 0, that's the maximal homomorphic subspace in the tangent space in the zero locus. And we identify this H with the affine subspace Z1 is equal to 0, which is tangent to this. Yes, we identify. And now, let us evaluate, let us restrict phi to H. Phi to H, restricted to H, what is it? This vanishes identically, and we have only this. It is equal to L of Z, Levy form. Now here Z, for us, this is Levy form restricted to our H. Being restricted to our H means that 1 is already equal to 0. Means, so let me call it Z tilde, via Z tilde. Z tilde means Z2, etc. Zn. Just n minus 1 coordinates vector. That's it. And we know that it is greater or equal than some constant times the square norm of Z. Because L is positive definite. And we obtain that phi is strictly positive on H outside the origin. Outside the origin. And conclusion. There exists a positive R such that the intersection of H with the ball of radius AR, center of X, lies outside, so with punctured X lies strictly outside Cn, outside the closure. The situation is like this. Here is this intersection. Here is our X, here is our D. Because of what? Because Levy form is strictly positive, and this implies that the function phi is strictly positive in some punctured neighborhood of X in H, because the remainder is much smaller. And now let's call this S. Let's call this the surface S. And that's it. That's just a ball in complex subspace. Now let us approximate this ball by a sequence Sk of balls just shifted up. And Sk converges to S. The boundaries also converge. And the boundary of S lie inside in the complement. Inside the complement. Yes, and that's it. And now actually we don't need Sk. Why should I? We don't need them. It's S. We are happy. We are just fine with just having S. And what we can do? We take f, the function f of z, to be equal to z1, right?
Okay.
And we know that the restriction of the function f to a small neighborhood of point x, here f, so here, let's denote this neighborhood by u, f u on d doesn't vanish. Because the zero locus of f is here. Zero locus of f is this hyperplane tangent to the boundary. And so, therefore, strictly inside, f doesn't vanish.
Yes.
I would say that f restricted to d. No, u with d because we are doing local analysis.
Yes.
Okay. Yes.
So, and then we use.
And then we use this criterion.
Okay, so.
This is sufficient condition.
So
yes.
The boundary.
Yes.
Have a small neighborhood.
That's it.
Yeah.
Yes. And then, so then, by proposition 1, D is holomorphically non-extendable at X. So statement 1 is proved.
So really we don't need this intersection of H and the R?
Yes, we don't need, but we don't need. We need it for the following reason, because we know local behavior of D near X. Because we know actually we don't need very strong assumptions that if D is globally defined like this. So if we had this global assumption, I need not consider intersections. But I would like to emphasize that we are able to work in weaker conditions, just working only in the neighborhood of the point X, and consider that locally D is given by some level set in some neighborhood. Because D may be something like this, something strange. Here we are fine, here we are not fine, but here, yes, and here we take the intersection of neighborhood. So statement 1 is proved. Let us prove statement 2. So proof of statement 2. Suppose we prove by contradiction. Suppose contrary. Contrary means that there exists the uniform is not non-negative definite. This means that there exists one-dimensional subspace lambda contained in H, such that the Levy form on lambda is negative, meaning that the Levy form on lambda of VV, Levy quadratic form, is less than or equal to some minus some constant of the times and the squared norm of V. Saying that Levy for that Hermitian form is not positive definite means that there exists such a subspace. So and let us consider without loss of generality that lambda is given by the same equality. Lambda is the x-axis. So our subspace is H is the Z1 is equal to 0, right? Yes. And let us consider that it is the Z3, etc. equal the Zn is equal to 0. So we consider that basically lambda is Z2 axis. Because it lies already in the zero locus of Z1, in the hyperplane Z1, Z2, etc., Zn hyperplane. And we just reorder coordinates. We just make a kind of coordinate change in the space, which may be made affine coordinate change. So yes, that's the Z2 axis. And that's it. And now let us restrict the function phi to lambda. The restriction phi to lambda is equal, so this cancels out, the Z1 is 0, the Levy form is less than or equal to minus C times the modulus of Z2 squared. Just we can put appropriate constant, not exactly this, but not doesn't matter. Yes, plus A, but actually it will be this constant. Plus lower terms. plus lower terms. And therefore, it will be strictly less than 0. And therefore, the situation is like this. Here is our domain D, and here we have lambda, our lambda. And here is our Z1 axis. And we can again intersect with small neighborhood, lambda with a small neighborhood. We do the same trick as here. In order to make sure that this intersection disk will lie strictly with the tangency point x deleted, lies strictly inside D. And this will be our surface S. So lambda, this will be our lambda intersected with U. And
okay, so disk is an intersection of A and U?
Yes.
Okay, and
We take just small disk on this line, centered at the tangency point. That's it. And so we denote lambda intersected with U. We denote it by S. This is our surface S. And we would like to show that this is our contradictory compact surface. What we have to show? We have assumed that Levy form is negative, is not positive definite. We would like to prove that D is not locally L-convex at X. In order to prove that it is not locally L-convex at X, we have to provide a surface, a compact surface S passing through X, in such a way that its boundary lies inside D. And it is a limit of a segment of compact holomorphic surface lying strictly inside D. And now what we do? The surface S is already constructed. Its boundary is okay, it lies inside D. And its only intersection point with the boundary of D is just the tangency point X. And now, what is K? So here is our S. Here is our, sorry, it's not this. That's our S. And now, Sk is something very straightforward. Sk is S. Sk is S minus 1 over K, 0, etc., 0. We just push down in the coordinate Z1. And and look here. This guy becomes negative. And this, what is this? And this is what is this, actually? This Levy form. This is Levy form evaluated at Euler vector field, right? And we would like to make sure that here we remain negative. Yes, that's it. So let us evaluate phi on these points. So we know that we know that phi of 0, Z2, 0, etc., 0, we know that it is equal to the following. It is equal to
minus 1 over K.
By the way, we can write down because since remission form in one variable is just squared modulus up to constant factor, right?
Okay.
We can write down that it is equal to minus z2 squared plus higher terms right? And now we would like to add the 1 over k. minus 1 over k. And we evaluate. So phi of 1 over k,
Change our formula.
z2, 0, etc., 0. How does it look like? What is this difference? And we apply Lagrange increment theorem. Because we know this restriction. And how to obtain this value from this value? This value minus this is equal. So we are evaluating real valued function, right? If we know that it is equal to here is we have minus 1k minus 1 over k times the phi the x1, where x1 is the real part of that1, right? At some intermediate point zeta. It's just a Lagrange theorem.
Yes, okay. Why x1? Okay, x1.
It's bad notation because x is already, we use already x.
Yeah, okay, but I understand what you mean.
Yes, because actually we shift along the real z1 axis. We differentiate along the real z1 axis.
So it is basically like a real part of z1.
Yes. And that's it. And we know that at x, that there is derivative is positive. And therefore, in some neighborhood of this point, yes, because we are dealing with real valued function in real valued variable. Now we put the imaginary part of z1 equal to 0, and we change only the real part. Okay. We differentiate. Let us write down properly the real part. Real part, z1, like this. We are dealing with function of n minus 1 complex variable and 1 real variable. And we differentiate in real variable. And we know that this difference is equal to some to minus 1 over k times the derivative in this real part at some intermediate point, right? And this positive, since at the point x it is positive, we can shrink our neighborhoods in order to make sure that this derivative will be positive everywhere in the neighborhood.
Ah, okay.
Because function is.
So we have that this difference is negative.
Yes, negative.
Okay,
and therefore the values of the value of the function phi takes strictly negative values on sk.
Because it was negative.
Yes.
Yeah, okay.
It was non-positive, but it becomes negative. And therefore, this implies so I'm not writing details on epsilon delta language using by intersecting with proper bolts, etc., but it's quite obvious. This implies that phi restricted to sk is negative. This implies that sk lies in D, but sk converges to S, and that's the end of proof.
Okay.
Because it's the definition of sk, and it's obvious that sk converges to S, sk tends to infinity.
Okay, SK
SK is this.
Yeah. So SK lie in our domain.
Yes.
And,
They converge to S.
And they converge to S.
The boundaries converge.
For convexity, we want that they
Don't lie to
don't lie
all.
in our domain.
Yes. And this finishes the proof of the second statement of Lévy-Strauss theorem.
Okay, so it's just that the concept of convexity is not very intuitive a little bit.
The concept of L convexity.
L convexity means that our domain, that for every complex surface which
Passes through boundary point.
touches our domain,
Yes.
we have another complex surfaces which don't lie in our
No. Actually, the contrary to L convexity means that there exists a surface touching the boundary of our domain, and whose boundary, the boundary of the surface, lies inside. And there exists a sequence of other compact surfaces converging to it, this boundary. But such that each surface in the sequence lies entirely in D. This is L non-convexity.
Okay, so and the convexity?
But L convexity is when such sequence doesn't exist. Where for such
it doesn't really clear why we have null convexity here.
It doesn't really care why do we have no. Yes, because here
why do we call it convexity?
Convexity because consider the case of lines.
Okay.
Consider the case of lines. Consider the case of planar domain. A planar domain is called convex if one can touch it by a line through a line entirely outside at any boundary point, right? A domain is not convex at a certain point if we can touch it by a line segment lying inside our domain, right? In this case, we can shift this segment downstairs and consider a sequence of segments converging to it, lying inside. This is non-convexity in the usual sense. Yes. And this is convexity, meaning that if we construct that for every line passing through this point, even if it is tangent, we can, for every segment of lines, segments converging to it, starting from certain k, the segment of the sequence does intersect our domain. This is the intersection locus. It's non-empty.
Okay.
Yes.
So it doesn't lie in our domain, but still it intersects.
Yes, still it intersects, yes.
Okay. Yeah, now it's better.
So now let us. So we have proved some local results on condition of convexity, of different types of convexity, and now we will be dealing with functions whose levels with globally defined functions whose sublevel set is guaranteed to be non-extendable, to be domain holomorphic, whatever. These functions are called plurisubharmonic. Have you seen harmonic and subharmonic functions in complex analysis? Maybe not subharmonic.
Not subharmonic, but
okay.
harmonic functions.
Okay, let us recall this material. Okay, let's recall this material. Definition. let us consider the case of one complex variable. A function is called harmonic if for every point x in domain and for every r small enough, one has the following inequality. The mean inequality. So harmonic. No, sorry. One has the following equality. U of x is equal to 1 over 2 pi. The integral over z minus x is equal to r. U of z ds. Here the ds is the length element on this circle.
Here.
Just, yes. This is the mean value along 2 pi r, I would say, like this. Or one can write down in the following way, equivalent. X plus r e power e theta, d theta. It's the same. That's mean equality.
But then if you have phi, not
So sorry, phi. I'm sorry. Thank you. So sorry, phi. And phi is called subharmonic if the same is true with inequality. So there is a following theorem. Phi is, let phi be C2 smooth. Then phi is harmonic if and only if the Laplace of phi is equal to 0. The second, phi is subharmonic if and only if the Laplace of phi is greater or equal to 0. Have you seen these statements before?
yes.
And the second as well.
I don't really sure that we had some harmonic functions, but
But okay, let us review very briefly this material.
well,
How have you proved? How could you prove this?
well, we use this equality and then I believe just use it for counting our Laplacian.
How do you deduce Laplace equation from our equality? Okay, yes. Mhm. Actually, we can use the previous material.
Well,
A kind of previous material. Oh, yes.
okay, so
Okay.
we may write a different function as a series,
Exactly.
and then
Yes.
we will have the series, then we take the lesson and disadvantage to prove that it will be 0.
Exactly, yes. So we, we do the following. We write down the expression phi of, let us consider that x is the origin, and let us prove that the Laplace, let us prove that if phi is harmonic or subharmonic, then the Laplace at x should be 0 or non-negative. So subharmonicity implies Laplace is 0 or non-negative. So x, let us x be the origin, and then phi of z, we can write down this linear part after a change of variables. We can write down that it is real part of some constant times z plus Levy form, which is now b z squared plus higher terms, right? And what is b? b is equal to d squared phi dz dz bar. And we know that it is 1 over 4 of Laplace of phi. This is well known form. I think we have had it in complex equations, right? And then the integral of this guy along the circle vanishes for quite obvious reason. But this is the integral of phi 1 over 2 pi integral of phi is equal to what? Is equal to b r squared plus O small of r squared. And we know that this is have the same sign in b. So harmonicity implies b is equal to 0, right? Subharmonicity implies b non-negative. That's it. So this is one way. The other way, let's prove the other way. Suppose the Laplace is as we want. Let us prove harmonicity of subharmonicity.
When we have from our lesson, then we have that b is
B0 is something indefinite, because here we have some known terms. B0 is something in between. If B is non-negative, then everything is fine. If B is strictly positive, then everything is fine. But if B is 0, it is something intermediate.
Okay, we have the lesson. So goes to 0. So our derivative is 0, and what do we have down that? To this.
So we suppose that Laplace is 0 or non-negative. We have to prove the equality or inequality.
Can we use
We cannot because actually we know that suppose we know that Laplace is vanishes. How can you now you have the following? You have that this integral is equal to b to high terms, but you don't know what is the sign of these high terms.
Okay.
Just a priori. Have you had a partial derivative equation course?
No.
Okay. You will see some energetic inequalities or equalities, some integral inequalities. But here, I would like to say that we can consider this function. Let us call this function psi of r. We fix x and we change r. Let us call this function psi of r. We know that psi of 0 is equal to phi of x, right?
Okay.
And now we would like to investigate its behavior for non-zero r. In particular, we can consider it taking its derivative. Phi prime of r.
We have. Okay.
We can differentiate the integral, right? What is the derivative? Yes, we differentiate. It's the same integral. And here, what is the derivative? D phi. Have you seen Green or Stokes formula?
Yes.
This flow with flux through the boundary and yes.
Yes.
That's the whole issue.
Okay.
Okay. So now what do we have? When we differentiate in R, we obtain the following.
Okay, so we have derivative of
D phi over dn. N is exterior normal.
Yes.
This is the derivative on O in R. Times
exponent.
Times exponent, right? The derivative from just one moment. Let me recognize this integral. Let me write down like this. And we obtain this, right? And we know that it is the integral of divergence. The integral of Laplace. Here we have the vector field, which is the dphi over dn, right? And we know by well-known Stokes type formula that this is equal to the second integral of Laplace phi. Do you know this formula? And we know that Laplace is either 0, and in this case the derivative is 0.
Okay, so
Or negative, then the derivative is not negative, then it is, we have inequality of subharmonic function. And that's the end of proof.
okay.
So now, I would like to explain the word of subharmonic. So etymology. Consider Dirichlet problem. Do you know what is the Dirichlet problem? Dirichlet problem. So the problem is like this. Given a domain D, for example, with smooth boundary, and let us consider function psi on the boundary, continuous function. Find harmonic phi on D, continuous on the closure, and whose restriction to the boundary is the given function psi. Proposition. Let f subharmonic with the given boundary value. Then f is less than or equal to phi. Subharmonic means its graph is below graph of harmonic function. Yes, that's it. So the picture is like this. Here is our harmonic function. Here is graph of phi, and here is graph of f. I suggest to prove it for the proof for D being disk. So let us take D being disk, and 0, let us take 0. The inequality f of 0 is less than phi of 0 is obvious because phi of 0 is the integral, is the mean value. And the mean value is defined by the given boundary condition. Right? Mm-hmm. And as in the surface of subharmonic, its value at the origin should be less. Right? Okay. And if how to prove it at arbitrary other point? Very simple. We can use conformal map, conformal automorphism of the disk, sending any given point to the origin, and apply the same argument. Because notion of harmonicity is invariant under the holomorphic change of variables, because of the equivalent formula for Laplace, because of this formula. Yeah. Okay, that's it. And now we have some time. We have some time to introduce pluri-harmonic functions. Let me say something about maximum principle. Maximum principle. If phi is harmonic on D and continuous on the bound on the closure domain, then if phi achieves its maximum, then this point where the maximum achieved is lies above the boundary, provided that phi is not constant. So if phi is not constant, then it achieves maximum only in the boundary. And this follows just from mean and subharmonic as well. So harmonic of subharmonic. Because of this, because for harmonic or subharmonic function we have either equality or inequality, and it's clear that it's clear that if a maximum is achieved at a given point, then it achieves on the whole circles, on the whole circle as well, because on the whole circle the value is equal to the same maximum. That's it. And the function is constant. Now let me introduce pluriharmonic functions. Definition. Now let us consider a domain D in Cn. A function phi, a real valued function D on domain, is pluriharmonic or subharmonic if for every line L, for every complex line L, the restriction of the function phi to L intersected with D is harmonic or subharmonic, respectively. That's it. So example, basic example, so the x1 x1 is harmonic. This is also harmonic for quite obvious reasons. And proposition. Let, or theorem, I don't know how to call it, but theorem, let phi be C2 smooth. Then phi is pluriharmonic or subharmonic if in a Levy form is the extended Levy form is vanishes or non-negative definite. The proof is very straightforward.
Well, I believe it's like with one-dimensional case.
Yes, it is just it is immediate reduction to one-dimensional case. You take the line and just vanishing of positivity or non-negativity of Laplacian is the same as vanishing of non-negativity of the Levy form restricted to the line. And that's it. So why it is interesting to consider the subharmonic function in our case? So theorem. Let D be a sublevel set of plurisubharmonic functions. Then, for example, plurisubharmonic on all of Cn. Then D is holomorphically then D one can show that there is a theorem saying that D is holomorphically non-extendable at each point, just holomorphically non-extendable at the boundary point. And by Oka, D is domain of holomorphy. So how to prove this? The tricky case is when phi is not strictly, so one can say that phi is strictly pluri-subharmonic if the Levy form is strictly positive definite. In this case, we would call it strictly. If phi is strictly pluri-subharmonic, and if phi has different non-zero differential at the boundary, then we can apply the previous arguments, Levy-Kshostka theorem, which says that in this case, at the boundary point, we have non-extendability, right?
Yes.
But actually, the theorem holds in the more general case, in this case. So what's next? I think we have already to finish.
So the tricky case, it is non-strictly.
Non-strictly, yes. Yes.
Yes.
And also we have a maximum principle. Proved in a similar way. And we have the following property. That if you have notion of plurisubharmonicity is invariant under holomorphic change of variables. Because we know how does the Levy form behave. We know functoriality property. So it doesn't change. And moreover, the restriction of a plurisubharmonic function to a complex submanifold is also plurisubharmonic for the same reasons, because the Levy form is a restriction. And we have also the maximum principle, also for the same reason. So a plurisubharmonic function achieves, a non-constant plurisubharmonic function cannot achieve maximum inside the domain. Because if it is maximum, then it will be a local maximum along each line, and it will be constant along each line, but it will be locally constant. That's it. And Alexei will present some nice exercises about plurisubharmonic functions. So yes, actually, do we have some time left or not? A few minutes. One moment. Because if you have a few minutes, then I can present some more material. 2 minutes. Okay. 2 minutes. Okay, and I would like to say the following, that the holomorphically convex domains are extremely nice domains in a way that they can be embedded as complex submanifolds in Cn. Because not every complex domain can be embedded as a complex submanifold in Cn. Because a necessary condition for this that our domain be a domain of holomorphy. Because if you have a true submanifold in Cn, then coordinate functions cannot extend beyond our domain. Because the domain is kept to infinity, and there is at least one coordinate function that does not extend. So going to infinity means sum of coordinate function goes to infinity.
So any submanifold should be a domain of holomorphy.
Yes, and the converse is true as well. Any domain of holomorphy does embed itself as a submanifold.
And so that's why we like harmonic functions, because they provide us domains of holomorphs.
Yes, yes, that's it. And so if you have sublevel set of plurisubharmonic functions, then it can be realized as a submanifold in Cn. And those domains that are realized as submanifold in Cn, they are called Stein manifold. Многообразие Штейна по-русски. Stein manifold. And this is Stein theorem stating that every holomorphically convex domain, or equivalent domain of holomorphy, can be realized as a submanifold, can be embedded as a submanifold. And it is even more stronger than that. If we have, there is a notion of holomorphic convexity for domains for manifolds. So a manifold is called holomorphically convex if the holomorphically convex hull of complex subset is a compact. If we have such a property of a complex manifold, plus some extra conditions that there are functions that separate points, or something like this, then under these assumptions, Stein's theorem states that the manifold does embed the submanifold in Cn for n big enough. It's very deep theorem of multidimensional complex analysis. We will not prove it, but we will see some its aspects, maybe, if we have time. So let me stop here.
So we want our domains be submanifolds because with submanifolds we may use some.
Yes, it's always nice to
submanifolds and
yes.
use coordinates there.
Yes, actually being submanifold is actually the same as having a finite system of functions such that go into the boundary means that some of the vector functions formed by them escapes to infinity.
Okay.
That's it. It is something like being domain of holomorphy, but in the domain of holomorphy we have one function which escapes to infinity along sequences conversion to any boundary points. But now we have to in order to have submanifold, we have to have uniform conversions to infinity in a way. That's a big difference, and Stein's theorem states that it's possible. Саша, хотите что-то обсудить? Пока еще не время. Нет, хорошо, тогда дальше.
Если будет в пятницу?
Да, пятница будет, да.
Тогда, наверное, где-то в 17 часов.
Да, в пятницу я буду. Единственное, что у меня самого будет доклад, я должен еще поработать. Я не знаю, кстати, будет ли у меня время на обсуждение.
Ну хорошо, это
Ну, что-то придумаем. Да, если будет желание что-нибудь коротко обсудить, то коротко обсудим. Вот. То есть просто у меня время будет ограничено, но обсудим. Хорошо.
Мы кого-то ждем? Нет? Угу. Так, хорошо. Okay, so let us consider a few functions. Okay, so let me write down a few functions, and so the question is if these functions are pluriharmonic or plurisubharmonic. And this is
Actually, so we have to show.
Okay, so basically I need to count live forms.
Yes, actually we have the harmonicity also harmonicity harmonic condition is condition which should be satisfied at each point.
Okay.
Condition, and
So,
check it.
so. Okay, I don't need to.
so in A we may do this either in real coordinates, just represent Z as
Maybe it will be easier, but it's just square root of that.
mhm.
That.
Yeah, and D well, it's up to a constant, the Laplace operator in these coordinates.
Okay, so D squared. Yes.
Саша, вы сейчас, вот, мне кажется, первый пункт, вот появляется модель. Самый такой.
Well, у меня есть ноль.
Okay, sorry, one more, sorry, кажется, speak English.
Ну, мне кажется, что у меня получается ноль. Соответственно,
So, I agree with you that it will be zero, the Laplace will be zero at the places where it is defined.
okay, yes.
I'm sure that the Laplace is defined everywhere.
Well, that is not zero.
Laplace is zero everywhere, that's true. But I mean that the Laplace, I'm sure that the Laplace is well defined. I'm sure that the function is theta smooth. It's modulus of z. Theta smooth. At which place it is theta smooth?
Okay, so it will be C2 smooth if z is not zero.
Exactly. And I agree with you that outside the zero, Laplace is very ranges for quite obvious reasons.
Okay. And
Yes.
so we need to understand what will be.
But still, have you calculated the Laplace and the Laplace vanishes?
Yes.
Okay.
So I basically have like 0 over 4 that how do I call it?
Can you write it down?
I have something like that. So then I have. So it will be okay. Something like that. Let's see.
So, and what is the answer? What is Laplace? 0. Okay, because what I have to do, we have to differentiate first in z, and then in z bar, right? When we differentiate in z, the square root of z bar remains, and what about z? It goes down.
Okay,
The
yes.
square root of z goes down, right? And then we differentiate in z bar. Z bar goes down, and I show that we obtain 0. Sorry?
Maybe I have problems with differentiation, but I believe that it will be strange. Okay, so okay, and then
As a hint is that if you take the log of modulus, then everything is fine. But if you differentiate, if you take Laplace of just z, then we will obtain something on the
okay, but don't just step away.
But just differentiate. Because what is this? What is this expression? It's the square root of z times the square root of z bar, right? It's a product of two functions, one of z and one of
Yes,
z bar.
I know.
And we differentiate
Okay.
this product in separate variables, z and z bar. And you differentiate first function in z and the second function in z bar, and you write down the result and multiply it back. What you get?
But
But maybe it's easier to do in these coordinates.
Well, okay. Maybe I miscalculated and I need to.
But have you found a mistake in this calculation? There is a missing coefficient. Missing coefficient.
One sec.
Does at the very end there is missing coefficient?
Yes, one sec. So. No, okay.
The coefficient 2.
One second. I just. Okay, and then I have.
What I believe the expression is like this. It is equal to square root of z times the square root of z plus. Modulo just possibility to multiply it by -1, but doesn't matter. Locally it's basically the same. And what you do is just differentiate this squared, the z bar of this stuff is the square root of the z times the square root of the bar, the z bar. Because one is holomorphic, the other is one holomorphic. Right? And we obtain, this is just, and we obtain on 0, we obtain 1/4. We obtain this. Yes. Because this makes 1.
One half. Yeah.
It's -1. Yeah.
-1. I think it will be rather 1. No, because the problem was with the first coefficient here. There were two terms, and here there was missing the coefficient.
Yes, I found it.
That's it will go. But this calculation is very straightforward. It's just you just differentiate function of one variable. And here there was missing coefficient 2 here. And it was 2.
And that's why the.
Yes. So this means that this guy is non-negative, right?
Yeah.
Outside 0. So outside 0.
Yes.
Outside 0. So in the complement of the origin, it is subharmonic, right? What about its behavior at the origin? Can you show that it is harmonic and the harmonicity condition is very satisfied at the origin? Of course, you cannot differentiate from the origin because function is not C2 and even not C1. But maybe we could hope you can return back to the definition of subharmonicity without derivatives. Just mean inequality, and to prove that the mean inequality takes place at the origin. It takes more circles, so it's simply at the origin, and you ask whether the mean inequality takes place.
And for 0, I believe, so we will have this integral as it's from model that then integral will be non-negative.
Yes.
So it means that we have, and in 0 we will set it 0, so we have a subharmonic function.
Yes, but then the function is subharmonic because every condition is satisfied at each point.
Mm-hmm.
Yes.
And you can pick an example given here and you calculate and complete for the easiest examples.
Well, I believe the second one is quite easy because we have two models, so then our inequalities hold for each part. So then, as derivative is linear, then of course we will have that Laplacian is non-negative.
But in fact, in the expression of derivative del squared, it's the expression of Levy form.
I will have terms with
Yes, Levy form. It's the expression of Levy form.
But I believe that they will be 0 because
No, Levy form will be non-zero. And moreover, when you calculate Levy form, then at certain moment, intermediate coefficients, some intermediate coefficients will be negative. But maybe they will not influence the whole expression. You have to calculate.
okay.
Actually, I believe that we will not have time to solve all the items, all the items. No, just several ones.
Okay.
Because we have still some other problems.
Mm-hmm.
Both areas. You mean second, you mean modulus Z is modulus W, yes?
Yes.
Yes, that's easy. Then we
Mhm.
yes, I agree that it's easy because
Well,
some-
we have this mixed derivatives, they will be zero.
they will be zero. And
Okay, and
yes.
so we have just some
There.
two.
Yes, we formatted it there, and this positive.
Yes,
and
so
negative.
then we have some two non-negative parts like
Yes.
this true and everything is good.
Okay, so there is no problem with the last operator, which is fine outside the origin. And what about the origin?
Okay, and with origin we can have integral from some of moduluses, so they are.
Yes,
They are non-negative, so then we have
Yes.
integral non-negative, so then
along which do we integrate? Along what do we integrate? Which is the integration concept in this case.
okay, so then I will have kind of polydisc, I believe.
Doesn't matter. So it's
Well, I will just take a direct product of two circles.
No, because mean inequality is for functions of one variable, right?
Okay.
And we have defined perfect harmonic function as a function with restriction to each line,
Mhm.
right? Then you have to check whether it's the restriction to each line from the origin.
Okay.
We have some harmonic.
So I choose a complex line and
And right is
circle.
yes.
And there I still have that line equal to close, so
Yes, and now you can choose one or two among the answers.
okay.
I suggest to choose E because it's nice.
Well, yes.
Because F is kind of trivial, but E is nice.
Mm-hmm.
That was kind of true.
You see why it's trivial.
Well, okay, I have. Okay. So I just go to real coordinates and then I can.
Yes, because the function.
Okay, so I have like real coordinates and there I count my lesson and I have 0, I believe.
Yeah, because real part of Z is 6 and real imaginary part of the algorithm is 1.
Yeah, and then I have one second derivative and it's 0, so
Yes.
0, so it will
Yes.
be just harmonic.
Yes.
Not an sum.
What about E?
Okay, what is it? Well, let me have a few moments and I will try to calculate it. Okay. So basically it will be Z1 plus I Z2 and W1 plus I W2.
Minus.
Minus I W2? Yes, minus. But then it will be just Z1 W1 plus Z2 W2.
Yes, that's it. Yes.
So okay, and now I take the lesson.
Yes, Laplacian along lines. Yes, Laplacian, yes, you can take general Laplacian, but it is not our framework because we are dealing
So, um, okay, so basically I need to count level 4.
Yes.
It's not this nice. Okay. What will it be?
You can, so I suggest that this is real part, right?
Yes.
Real
So,
part is complex.
may I work just with ZW lined and then to take the lesson for it? Well, to count level 4 for it, and then
Yes,
take a real part of it.
Yes, well, no. In fact, you have really to count the before. There is no, and now the question is given function which is real part of a simple complex function. How to count the before?
Well, I may count level 4 for the whole that W point, and then may I say that it will be just the real point of it?
Suppose our goal is to calculate some kind of derivative, complicated derivative of real part of the function. And suppose we know how to calculate this complicated derivative for the complex function. How to calculate the same derivative in complex variables for the real part?
Just for the real part, then
What is a nice way to go from the complex number to its real part, in order to preserve the complex nature of expression.
How do I take real part? Okay, so I may take f plus f
Exactly.
aligned and let
This builds a lot.
Okay. Okay, so I may just work with it, okay.
Mm-hmm.
And it will be z double line plus z line double.
Exactly.
Okay, yeah. Nice one. Okay, so then and for this thing I may count level 4.
Yes.
Okay, so I take this insert.
So it is. So you have to kind of.
Yeah, so it will be it seems like it will be 1 equally.
Can you just write down the this?
So let it be f. So And then I take like
You have to write down also multipliers the z and the w bar or something like this. At each derivative there should be multiplier.
yeah.
Yes.
Yeah, I just. I just missed in my notebook, so. Okay, this is here. Okay, so this 2 goes to 0. And for this one I have 1.
Yes.
So it will be. And this one is 1 true.
So it may put this there.
So it's something like.
Exactly.
Mm-hmm.
And this is on 0, right?
Yeah.
Therefore the function is not Lorentz harmonic. And it doesn't have a chance to be Lorentz harmonic. So of course the formula is not 0, but is it positive, or is it a negative definite, or something like this? Or this?
So what do we need for it? We need.
So basically what is written? A real part, 2 real parts, or actually the real part of the z times the w bar, right? Yeah?
No. One sec. I missed here.
Yes. Yes. And
So
so
it
we
will be-
finally we obtain the real part of the z times the w bar. And here this formula is no negative definite somewhere.
Okay, so this is again for our function, and now we need to understand is it negative error on the side?
Yes, it's no negative definite on each complex line. То есть no negative definite form. This is condition form. So the matrix is like this.
Okay.
But it is a matrix of negative definite condition form.
So I believe that that's quite, but so if I have multiple things, so then I will have just basically this. And, it is one negative. Isn't it? I just said that I may try to use my phone for two.
So attention, this is not, so this what you have taken is you have taken the reform restricted to the line that equals down, right?
Mm-hmm.
On this line, it sounds like positive. Okay.
Okay.
What about other lines?
Ah, okay. So I have lines. Basically, I may say that I may choose a line which sounds somehow. Lines.
that on each vector the quadratic form is non-negative, or to provide a vector on which it is negative.
Yeah, I understand.
Vector means two components, V1 and V2.
Yeah, I understand. It should be negative then on the whole complex line, yes?
Yes, because we can choose V1 and V2 arbitrary complex numbers. Can we choose them in such a way that if you substitute the vector V1, V2 to this form, we obtain some negative number? Real negative number.
Okay.
Because the form is a quadratic form. Is a real logic form. Hermitian form, Hermitian quadratic form. And always we use the values, and maybe sometimes it can take negative. It's possible.
Yeah, so
Well, I obtained just W and Z. Like
Yes.
they changed their places, and so for it to be negative.
So which is you have to write now the expression of the form. So you quadratic form, you get a vector value on unknown vector. Of the coordinate z. Suppose the vector has coordinate z now, right?
Okay, so I have complex line Z equals to minus W,
For example, yes.
and so then I have something but
And that's it. And then a negative one.
yes, basically we should try to find an eigenvector of this matrix which corresponds to the eigenvalue -1.
oh, okay.
Because it is symmetric.
Oh, okay. I just
yeah.
wrote it down here in some nice way and didn't see how to take an example. I just tried to write down what we have. So I just said that I will have something like that here. So here I will have something like that, and then it will be counting down, and obviously this one is real, so I will choose any A in such a way that this sum will be negative. And if B is 0, then this part is 0. So basically I may choose any A such that its real part is negative and everything will be negative on this line.
Okay. Okay, let's see. Maybe I suggest that you will present the next problem
Maybe even it is better to go straight to the third one.
Yes, that's nice.
Yeah, I guess. So let's.
Okay, so we're part of this.
It can be done as control.
Okay.
Let D in C and B simply connected domain.
As nice as you want. For example, suppose 1 and 7.
And let f be a pluriharmonic function of class C2. Harmonic. So f in C2 of D. So show that there exists a holomorphic function say H such that f is equal to the real part of H.
F is a real part of H. Okay.
Yes, don't you expect that this is a real part of holomorphic function is always really harmonic? For part of
Okay,
this
and
field.
F? F
This
is
is
a real
conventional
function.
stuff. About the converse, we'd like to show you to solve the converse.
Yeah, so f,
Is F a real function?
yes, it is.
Okay. Harmonic real function.
Yes. Real part of 5. So anyway, we have to find a candidate for imaginary part of this holomorphic function.
So we have F.
Yeah, so if F is Flory harmonic and also C2, so
So it's harmonic on a complex line. So it's less than whatever.
yeah, so we have
Complex line is 0. Okay.
yeah, so for C2 functions, this is equivalent to vanishing of DD bar.
Okay, so
So now we have to use somehow this condition.
Do you know a formula how to restore imaginary part of the function in the case of one variable?
Well, I remember that there we had something like we may take a partial derivative in x and in y, and then use them as a real and imaginary class function and do the Golota function because your equations hold.
And how do you found the function? Yes, and how do you found the function?
Okay, so it's a Golota function, and then for this Golota function, the real part is a partial derivative in x of a given one. So then it was integration, I believe.
Can you write down the integral in the case of one complex line? Suppose we have the harmonic function in one complex line.
Okay, so
And one of the imaginary parts corresponding to
okay, so if I suppose that f is one variable complex function, then I may okay, so then I may partial derivative mix, partial derivative from y. Okay, so this will be some function. And now I need to. And so I know that it will be dash mix will be so then I need so if we check
over dx.
Okay. And the no, I don't agree because the integral, differentialize the integral. This means that you integrate long path, some differential form long path, right?
Okay.
But in order to that this integral be independent of choice of path, you have to make sure that the one form is closed. The differential is there.
Mm-hmm.
Okay.
I doubt that this differential form, the f over the y dx, is closed. I'm sure that it's closed.
I'm not. Okay.
I'm not closed. Therefore, you have to integrate a closed form is a closed form.
Should be closed, so
I suggest to use both derivatives
well to
in the x and y.
okay. So
Which is the first derivative dx over the y minus minus the y dx.
one sec. Just
Well, nice idea. It's all the initial.
yes, but I just need to make sure that it will go right. So then I will add here. Okay, it will be okay because I will take this, yes. Okay, and for this one I need
Exactly.
derivative and it will be this.
Exactly. And then you.
I'm not sure about sign. No, it will be okay because I have here derivative dx, then I choose.
Yes, because
I reverse order and then I have double minus. Okay.
yes, and with the advantage of this form that if you differentiate, you take differential to 0.
Yeah.
Because the function is harmonic. And now our goal is to show that this is indeed imaginary part of the holomorphic function. This real part.
Okay, so if I.
So this function is well defined as integral because it is independent, path independent.
Yes. It's closed one, so it's okay. So.
And now you have to show that this function, together with the real already known real part, it gives a true holomorphic function.
Okay, so if I have this thing as an imaginary part, then if I take a partial derivative in x, okay, just seems that well, I may divide my integral into parts. Linearity, and then the first one will be 0, and the second one will be right this thing. And I wanted to use imaginary part.
Because if you integrate closed form of type a dy plus b dx, then this form is closed, and the derivative of the integral is clearly partial derivative in y and z.
Yes.
That's it. And it's very straightforward that we immediately Okay. And so this is about one variable. And how
what?
Yes, so you have done the case, everything in the case of one complex variable. What to do in the case of purely harmonic functions, in the case of many variables, for example, two variables? How to organize appropriate integral for the imaginary part?
Well, it seems like I need to do something same.
Yes,
As
something
in-
the same, but maybe you
Okay,
can
but-
make some.
Will it be okay?
Yeah, so you need to find a closed one form. So I think that we don't have much of a choice here. So we have f and we
Well,
have
yes. I just
derivatives.
I wasn't sure what it will work. But well, yes.
Yes, since you have just the domain in C, in Cn, so your usual differential is has 1, 0 and 0, 1 part, right? And if you just apply each of these operators to this form,
We'll have like four parts, and two will go
So this is 0 because d squared is 0. And this is 0 because f is pluriharmonic. And the same goes for d bar. This is 0 by pluriharmonicity, and this is 0 because d bar squared is 0.
Quadratic derivatives are 0 because well, okay, I don't understand why quadratic derivatives will be at 0.
Why this is true?
Yes. Like mixed derivatives are zeros because of harmonicity, and this is quite clear. And well, I wasn't sure about this quadratic part, so I didn't try this form.
What it's like in real, the round complex. We know real the round complex without this differentiation of real forms. It's the same because here what you do, when you replace d by d round, this means you replace differentiation d over dx by differentiation d over z. The formula remains all the same. The equality of mixed derivative is the same as in the real case. And this is equality of mixed derivatives in one of the other order. This implies that this equality that the round square vanishes.
Okay.
Because the operator d over the g, these operators commute because these are linear operators with constant complex coefficient.
Okay. Yes, of course.
So the solution is to make this the same the same argument.
Pretty much, yes.
Many variables. You just choose every complex variable, and for each complex variable you write down the same differential form. And use this, you sum them up. So you sum them up. These forms for each complex variable zj. You introduce xj divided by j. You do the same form, and you sum this form up through all the j.
Okay, so I have like
dxj.
there's a df minus the hat zj, and there is something more, okay?
Yes, d minus df dyj times dxj plus df dxj dyj. And I claim that the sum of this forms through all the j is the Schopenhauer's form.
Yeah, so you can do this in coordinates, but you can also do this pretty much without coordinates, just so using the Poincare lemma for the simply connected domain, you can write down df is this u. So in your domain, this is a closed form, therefore on a simply connected domain it is exact. So it's just
so we have this
not f, but something else, dg.
we use this argument about like, yes, okay. So we construct.
Yeah, so like this, you integrate.
Construct a closed form, then we say that it's exactly because we have simple connectedness. So then we may say that it's a derivative of something else.
Yeah, so and then it's pretty much, yeah, so you get a function like this, and then when you look at the decomposition of types, so you cook up function in the same manner, I believe. Yeah, so just need to produce the imaginary part, and this is done in the same way as in case of one variable.
And of course, you can wonder why this form should be closed in the case of many variables, because there will be terms of terms of coming from different J1 and J2, for example. And they claim that all these their contributions will cancel out, because otherwise the DB form would be not.
Oh yes, so you just need to represent D as partial plus D bar and compute the part which corresponds to each type. Okay.
Okay, so this G will be our imaginary part, basically.
I guess, yes.
О, спасибо.